In this lesson, we'll discuss another famous algorithm that's of great interest in current quantum research. The variational quantum eigensolver, or VQE, is a hybrid algorithm. It uses both quantum and classical steps to find the ground state of a system. In quantum mechanics, we describe systems by specifying a Hamiltonian. The Hamiltonian allows us to answer this question. For a given state, what is its energy? Equivalently, the Hamiltonian is that function that can be used to evolve a quantum state in time. It's all in the Schrödinger equation. In the Hamiltonian, we can encode the interactions between electrons in an atom, between those electrons and the atomic nucleus, and any other thing we want to include in our model of the phenomenon we're interested in exploring. As we know, one of the postulates of quantum mechanics is that the results of measurements of an operator are eigenvalues of that operator. Knowing the eigenvalues and eigenstates of the Hamiltonian is, in other words, what we would call knowing the states of the system. Nature is, in a way, lazy. All systems tend to gravitate towards a state with minimum energy. Let's ignore entropy for the sake of the argument. And because of that, in physics and in physics-related or inspired problems, one of the most natural questions to ask is, what is the ground state of the Hamiltonian? What's the eigenstate of the Hamiltonian that has the lowest energy? This is a simple question to ask, but in practice, it can be very difficult or even impossible to answer analytically. Complex Hamiltonians often come up in chemistry problems, where the energy state of a molecule is of interest. So it's common to see the VQE method used in quantum chemistry research. Because finding the ground state can be a difficult problem in complicated systems, we can try and do things by successive approximations to an initial guess that we think is reasonable. In the circuit model of quantum computation, a way to do this is to guess a pattern of gates in the quantum circuit that is parameterized. This means, for example, that the angles by which the quantum gates rotate qubits are not fixed. Instead, they are a parameter that we can tweak. Our guess for the circuit is called the Ansatz, which is a German word roughly translating to starting point. And the circuit we build is a parametric circuit. We can select values for the parameters and then execute the circuit. We get an output from the circuit, and we can then evaluate what the obtained energy value of that state is. But we want that to be the lowest possible value. Here comes the classical step. We update the circuit parameters, for example, by using the gradient descent method. We then run the circuit again and see what energy we get for our new state. We repeat this process several times until convergence. This, in a nutshell, is the VQE method. Now let's run a VQE algorithm in the Classiq IDE. We begin by going to the synthesis page and selecting the VQE model from our model library. The example here is to calculate the ground state of an H2 molecule. On the right-hand side, we have this already set up for us. By pressing Generate Hamiltonian, we can see it, represented as a sum of Pauli operators. We then generate the model by pressing this button here, and now we're ready to build our circuit by selecting Synthesize. The obtained circuit has blocks for setting the starting values for parameters and blocks for the ansatz itself. It's sufficiently involved for us not to dive too deeply inside. Instead, let's execute the circuit and see what we get. The plot below is a convergence plot. It shows that after a sufficient number of iterations, the parameters have converged to a value that gives us the minimum energy. Above, we can see the energy itself and the final parameter values. We've shown how to run a VQE algorithm in the Classiq IDE to find the minimum energy state of an H2 molecule. There are many more features in this module of the IDE and the Classiq platform, and you can learn a lot from reading the documentation. Hope you enjoyed this section, and see you on the next one.